at Continuum Analytics. I'm part of the high-performance analytic teams. So today I'm going to tell you how you can use GPU along within Spark and Python, and how you can write your own custom GPU code to speed up your per node performance. And throughout today's presentation, I'll be using Anaconda. It's a free Python distribution that includes the Conda package manager, so it handles all the Python and also non-Python dependencies that you may need in your working environments, and you work alongside with Spark. And this is the easiest way that you can get all the software that I'll be talking about today. So in this talk, I'm going to tell you why Python is a great language to use, and you can actually do custom GPU code within Python and inside PySpark. I'll be using an example image registration that I came up with that works within PySpark to kind of introduce all the different features that you can do. And I will end with some tips and tricks for using GPU within a PySpark. So why Python? So Python, many people think it's a very easy to learn language. It's very productive for people like DevOps, programmers, data scientists. And this is a great community. There are many useful libraries. There are many tutorials, reference materials, blogs. And it's very easy to interface with other languages. And if you're already using Python, you probably have already know this library, scikit-learn, is a great collection of machine learning algorithms. But people are thinking that, OK, Python is slow, it's interpreted. And the secret is Python is also used a lot in HPC or other data science applications where you need good performance. And what people do is they write the most performance-critical code in C, C++, Fortran, and then Python in the same libraries, the C types. It's very easy to interface with any C API functions that from your compiled language. But I'm not going to tell you to, OK, right now I'm going to switch language, write CUDA C to get GPU. Switching language can sometimes be very difficult, clunky, depends on if your team has the expertise, if it's originally if a team consisting of mostly data scientists, they may not know the compiled language that well, may not be able to do this very highly optimized numerical code in languages like C. And even if you have the resources to do so, it can get very tedious to iterate on languages that is compiled statically, and it's very hard to, with C++ templates, generate all the data types that you may use with Python. And how do you even use cutting-edge hardware so there are more exotic subset of languages that you may need? I'm going to tell you that you can do all of these in Python without ever switching language. So I'm going to show you I designed this example to be very compute intensive, and I want to use Spark to help me scale. So let's say we have a problem. We have a bunch of image fragments, and since drone is so popular now, we say we have a bunch of drones have taken pictures of a geographic feature, but I don't have the money to give proper GPS to these drones. So it's just pictures randomly orientated and in different scale. You kind of want to stitch them back together. And the simplest algorithm that I can think of is the phase correlation for doing image registration. It's an algorithm that is very heavy in using FFT. So that's how the basic algorithm and the application would look like at the end. The animation on the right is going to show you how the stitching process goes in each iteration. So you start with a bunch of small images. You want to group them together at first so that you don't do a lot of brute force image registration, which is in the green box. So after grouping, you have a smaller group that contains these images that are very similar. Then you kind of do a image registration across all the images. And then you keep repeating this process until you cannot fuse new images anymore. And I say in the blue box, in the grouping, we can simply use k-means clustering using the color histogram of the image as a metric to group similar images. And in the image registration part, we'll be using the phase correlation. We know that it's very expensive in computation, and it's very FFT heavy. And from experience, I already know that FFT is very good for performance, has very good performance on GPU. So to set up this experiment, you can use Conda from Anaconda distribution. So to create this one command to get all the software to create an environment for you, the Conda create. So that gives you, I'm setting to use Python 3.5. And Spark accelerate, which is a package that we show. It will actually help you install the CUDA toolkit. So that is a non-Python dependency. The only thing that doesn't help you do is install the CUDA driver. That you have to do it by yourself. And you can use that, just activate the notebook, and then activate the environment, and then launch it with IPython Jupyter notebook. And after some quick experiments, you will find that in this algorithm, most of the time we spend in this function, the cross-power spectrum, part of the phase correlation algorithm. And most of the time, from profiling, you find that most of the time is spent in doing the FFT. So there are actually 2 forward FFT on both images, and then it did kind of combine these 2 images and doing an inverse FFT to get the cross-power spectrum. So and we know that we can speed up this FFT very easily. And you can use Accelerate, the package, to really help you do that. So Accelerate is a commercial licensed library with a collection of hardware-optimized numerical functions. So like things like FFT, matrix multiplication. It has, for the CPU, it has simply optimized functions that uses MKL, and it has GPU accelerated functions that uses CUDA. Here is like a quick demonstration of using Accelerate, the FFT binding, comparing to, in the middle cell, comparing to the MKL accelerated FFT, and in the lowest cell, comparing to that is the CUDA FFT. And this machine is scaled from my laptop, very similar to this one, is a MacBook Pro. It doesn't have a very powerful GPU, but that already gives me 2x speed up. And that time is including all the host to device. Host is the CPU, device is the GPU. So all the memory transfer round trip. So that's very impressive. And in order to apply the CUFFT to our cross-power spectrum function, it's very simple. You just replace the FFT calls. I kind of highlighted in the red box. And I'm also highlighting in red because it's not optimal yet. It is doing a lot of CPU to GPU memory transfer. Like each of these calls is grabbing like F0, F1. They're all CPU NumPy memories, and they has to be transferred to the GPU, and then the result is copied back. And this is an in-place operation. It will just rewrite F0 and F1. And at the end, the inverse is the same. So there are 3 CPU, GPU transfer, and GPU back to CPU. And we can do better. And we can do better if we can make those computation in between these 2 GPU segments also working on the GPU. And we can do that with Numba. You can use that to custom GPU accelerated functions. So Numba is open source, it's free. And it's a Python JIT that doesn't replace the interpreter. It is a CPython library. So unlike PyPy, unlike Python, you can just import Numba from within any CPython. That's why it works with PySpark. PySpark uses CPython. And it uses, and it's special, and unlike PyPy, it doesn't compile the entire Python language. You're going to be specializing certain functions that are hotspots, and they are usually array-oriented, a numerical subset of Python. And our unique feature of Numba is that it's a CPU, it targets both CPU and GPU. So how does Numba work? In the very highest level, you can think of it as there's only one API. The JIT is a decorator. You can apply that decorator to a very compute-intensive function. Numba will do some static analysis at runtime. When you call this function the first time, it will use the types of the arguments to do type inference, then do the lowering in order to generate the machine code using LVM. But there is also another easier API for folks that are more into functional, more closer to functional style programming. It's the vectorized decorator. So in NumPy, vectorized generates functions that are called ufuncs in NumPy, universal functions. It's like a map operation for NDR arrays. So what happens here is you have some scalar function that operates on the scalars. It doesn't work on vectors arrays. When you decorate it, it leaves that function so that it works on any arrays of any dimension. And even the arguments, the input arrays, doesn't have to have a matching dimensionality. So there's a broadcasting rule to determine whether two arrays' dimensionality is compatible. And that's using the same NumPy machinery to do so. And with vectorized, you can easily switch between CPU and GPU target. So the function on top will run on the CPU. The function on below, which has basically the same body, runs on the GPU. That makes it very easy to convert your kind of more like array operations, creating array operations that works on the GPU. And if you do a quick comparison for the GPU ufuncs, the same function that I showed in the previous slide, on the GPU, it can do 4x faster. And again, including both host and device transfer, and on a not very expensive GPU. And that's because GPU has a lot of special function units that is specialized to work on things like transcendental functions, sines, cosines. It's all in hardware. So it's very efficient and very power efficient as well. When you use Numba in Spark, what happens is if type information is already available, like when you use vectorized, I can show that you can provide the type information there. It will compile your function into LVMIR on the client. So it's once on where you run your PySpark. And then it would send those IR to the workers, and then which would get finalized into machine code specialized for the CPU on those workers. That means if your workers have different kinds of CPU, some may have SSD, some may not have SSD or AVX, it will specialize to use the instructions, so you get better instruction generated for those workers, specifically for those workers. And for GPU, code compilation and code delivery, this is what happens. So you can see there's two paths. So only one of these paths will be taken each time. Normally, we may take the LVMIR and then kind of serialize, send to those workers, and then it will convert it to the PTX. The PTX is you can kind of think of it as an assembly, a portable assembly for GPUs. And then it would get finalized to the CUDA machine code, the CUDA binary. Or the other path, possible path, if it may already generate PTX. And if the worker has this same version of PTX, then you can just use that and finalize the final binary. And all this, the finalization would happen on every worker process. And if your task, if your computation is not intensive enough, this may mean there's too much overhead. So it's something to be careful about. And putting all this together into our CPS, cross-product spectrum function, now we can replace this middle piece with ufuncs that's generated specifically for CUDA. And you can even use specific memory transfer functions to move memory from the CPU to the host. So now our final function would be completely operating on GPU. So for some tips and tricks and experience that I learned when I developed this example, it's very important that you want to operate in batches when you use the GPU. So GPU is a many-core architecture. It's best to do very similar tasks all at once on many data. So because one of the reasons is when you launch a GPU function, which is called kernel, it's a significant overhead, unlike a normal regular CPU function call. So you prefer to use map partitions so that you have all the data for that partition ready and kind of copy it to the GPU, launch a kernel to compute on all of them, instead of using map, which will be handling one element at a time. Also, I want to find that using PySpark it would spawn one Python process per worker core. But due to the limitation of CUDA, the CUDA driver only allows one CUDA process using the GPU at each time. So it tends to underutilize the GPU. There's all the other workers are kind of waiting for the same CUDA hardware. Or even worse, you may be time sharing the GPU. So you'll be doing a lot of very expensive context switching on the GPU. One way to fix it is CUDA already provides this tool called MPS. You just need to know about it and launch it. It's kind of transparent to the application. So once you launch it in the system level, all your CUDA application will be beneficial to all your CUDA applications. It was originally designed for MPI by NVIDIA. Yet it acts as a GPU task server that merges all the GPU kernel launches into one process and then launch from that process. Another benefit with using MPS is it tends to reduce the memory footprint, the memory overhead for each worker process that uses the GPU. And for our example, in our example, we can observe in reverse for small data sets, we can already observe a 10 to 15% speed up for the application. So it helps you better utilize the GPU. So as a summary, and I'll show you how you can use Anaconda to create a Spark environment for experimentation. And also, Anaconda helps you manage its Python packages as well as others, like the CUDA toolkit, when you use it in Spark. And I'll show you how it accelerates for pre-built drop-in GPU functions that you can use, and Numba for when you need custom functionalities on the GPU when you're using PySpark. And thank you.